Good morning or good afternoon, depending on where you are. My name is Professor Orata. We are continuing with our thermodynamic lecture series. And today we want to look at eutectic diagrams for compounds. Remember, in the other lectures, we talked about simple eutectic diagrams. And the simple eutectic diagram, we had temperature, we have composition, A, B, we have composition, and we said that in this system there, if you did a freezing curve for some of these quantities, this is the freezing curve, then you will find, for example, this is the melting point for A, that's the melting point for B, and we are saying here we have liquid, here we will have B plus liquid, here we'll have A plus liquid, and here we have A plus B. That's just a simple eutectic diagram. This corresponds to the eutectic composition, which we denoted as XEU, and that is the eutectic temperature. Eutectic. That is where those two freezing curves, where these two freezing curves intersect. That is the eutectic point and corresponds to the eutectic temperature and the eutectic composition. Now, this is particularly simple. What about where we have formation of compounds? That is, for example, this substance A and B would react to form a compound. Let us say they form a simple compound where we have A to B, or we could have A, B2, and so forth. But let us look at formation of compounds. Eutectic diagram for compound formation. So, like we have said, we can have a case where these two react, and so what will be the eutectic diagram looking like? Let us see what it looks like here. So let's take a case where we have A, B, and then we have formation of a compound A to B. That A to B is a compound. And so we still have our temperature, and we have our composition, of course, XB, that direction, XA, increasing that direction. Here is 100% B, 100% A. Now, let us say the boiling, the melting point for that is TB, and the melting point for A here is TA. So what kind of eutectic diagram will we get when you follow? In other words, like we have said, you have the freezing curves, they intersect at the eutectic point. Now, what happens when you have formation of a compound? Formation of a compound. We will have a situation where try to get it drawn well. Now, if you look at this diagram, it looks like this is a diagram, this portion here is a diagram of a simple eutectic system. And this other diagram here is also a portion of a simple eutectic system. In other words, the two diagrams have been juxtaposed. In other words, it's like they have been fused together. So you have this This one for the simple eutectic diagram, and the simple eutectic diagram just fused at this particular axis for the compound A to B. So we have, as usual, that is liquid. These are the melting points for pure B, melting point for pure A, and the melting point of the compound. Now, let us label the quadrants. You are now familiar with that. If you followed our lecture on simple eutectic diagrams, then you are familiar with that. So in this quadrant here, we have A plus A to B. In this other quadrant here, we have A to B plus B. And in this section here, we have A plus liquid. Here we have A to B plus liquid. And here we have again A to B plus liquid and B plus liquid. So we have, these are the compositions of the various segments in this eutectic diagram involving compound formation. So we see that in the case of eutectic diagram involving compound formation, it's like we have fusion of several eutectic diagrams. That's in the case of compound formation. So let's just note that in the case of compound formation, the eutectic diagram is represented by several simple eutectic diagrams fused together. Fused or juxtaposed. Very important for us to note that. You have this and you have that. So, suppose you have formation of several compounds. Like, for example, you have hydration. You have several salts formed, but the hydration level is to different levels. Let's say that hypothetically you have copper sulfate, and then you have copper sulfate, which is hydrated, combined with 3 waters, combined with 4 waters, combined with 5 waters. That is copper sulfate, for example, pentahydrate. Copper sulfate, let's look at that. For example, you have copper sulfate pentahydrate. So let's just call that X. So that this X can be 1, let's say, can be 2, can be 3, can be 5. All those are compounds. They are hydrated compounds. They are not the same because the degree of hydration is different for them. And there are chemical consequences to that. Now, in this particular case, you're just taking the simple case where we have only formation of A to B. And then we have A and we have B. Like I'm saying, if we have several compounds formed, then we will have several simple eutectic diagrams fused together. Several eutectic diagrams fused together. So that in theory, for example, you expect that if you have formation of several compounds, that's formation of several compounds, then you might expect that you can have a system now where you have many compounds. Let's say that's AX1, AB1, then you have AB2, AB3, and each of these quantities, we are going to have, let's see, we have B here, we are going to have several eutectics, just like we have here for these compounds. We're going to have several eutectic diagrams for those particular ones. So you'll have, for example, one like that, then another one might be like that, another one might be like that, and that. All these are eutectic diagrams. So in this particular case, we can think of one eutectic diagram, second one, third one, fourth, and all fused together at the various points representing the compounds. Now we are looking at a simple formation of a compound here. Looking at a simple formation of a compound here. Now let us go to this particular one. One of the observations we see in the kind of eutectic diagram for the compound which I've just drawn here is you see that the melting point TB of A and B is lower than that of the compound. Just note that the melting point of the components, or the melting point of the compound, is higher than of the individual elements. So you see that the melting point here of the compound, let's call it TCPD, is higher than that of A than that of B. Now, suppose we take some isopleth. What is an isopleth? A line of constant composition, and follow the profile. Isopleth. That's a line of constant composition. An isopleth. So if we take some state point, let's take a state point, let's call this state point, let's call that state point P. And we want to follow the behavior of this isopleth. P, it will go through M, let's go through N, and then let's go through Q, let's go through R. So we are taking the isopleth P, M, N, Q, R. This is a line of constant composition. It's called an isopleth. Let us look at the profile along that isopleth, which you have written as P, M, N, Q, R. Let's look at this behavior of this along this isopleth here. Now, what happens? At state point P, we have the homogeneous solution, that's the liquid. And as we lower the temperature, we will reach the point M. So this, let's just write that down. But at P, state point P, we have the homogeneous liquid. And then when we reach M here, we will have the first crystals of A to B crystallizing out. Remember, in this section we have A to B plus liquid. So we'll have the first crystals of the compound crystallizing out. First primary crystals of the compound. Crystallizing out. As we continue, remember the relative amounts of AB2 and the liquid, is given by the Lever's rule for these segments. Remember Lever's rule? Lever's rule says that for the liquid here, the ratio of these two segments, this represents the liquid, that represents the compound. The ratio of these two gives you the relative amounts of these two quantities based on Lever principle. Based on Lever principle, we can determine the amount. You can check our lecture on Lever principle, which gives the relative amounts of these quantities in these particular state points. Now, as we continue, more liquid is formed, more compound is formed. And you can see more compound is being formed, given by this segment increasing. The liquid is relatively constant. So the liquid curve at this particular point, remember we have the eutectic points. These are eutectic points. Eutectic points. Again, I suggest that you make sure that you go through our lecture on simple eutectic diagrams. That's the eutectic point. So the liquid the liquid composition changes according to that curve there. That is M through E. Now, when we reach point Q, at point Q, what happens? At point Q, we have AB2, that's the compound. We have the eutectic mixture, and then we have A coexisting in equilibrium. So we have A, we have E, and we have A2B coexisting in equilibrium. Remember, we talked about phase rule. Again, that one is in some of our lectures there, which I encourage you to go through so that you know what it is. Phase rule says that F is equals to C minus P plus 2. But in this particular case, because we are keeping pressure constant, remember these two variables were pressure and temperature. So if you keep pressure constant, then the phase rule becomes C minus P plus 1. So in this region, we have three phases. A to B for the compound. We have that of the eutectic mixture, and we have A. So basically what do we have? For the two-component system, we have three phases plus 2. We have for the three components actually. We have two components in this particular system. We have three phases here coexisting in equilibrium at that particular point. We have three phases coexisting in equilibrium at that point. So the phase rule is given by 2 for the components which we have there, and we have three phases, 1, 2, 3, and we say that pressure is constant, that is 1. So the phase rule is 2 minus 3 plus 1. So this gives us 0, which means that the system is invariant, or the number of degrees of freedom is 0. Degrees of freedom. And that is the variance, F. This one here. Number of degrees of freedom is 0. So what does that mean? If the system is invariant here, it means that when we are at this state point, Q, there will be no change in temperature. The temperature will not change. The system is invariant. So it will keep steady at that particular temperature for quite some time. And then, of course, finally, the temperature will start decreasing. But now notice that when we go to this quadrant, as we move from Q to R, there is no more liquid. Now we have A and A to B. All of it has been converted, so we now have A and A to B. So we are here, what did we call that? We call that between at Q, and the temperature is constant. Just mark that down, temperature constant. At Q, we are saying now at Q, between Q and R, now we are just cooling A and A to B. Just cooling A and A to B. And note that there is now no liquid. Now, some relatively important observation with this compound formation diagrams for this system of temperature and composition is that there is some sort of a bearing on the shape of this curve here, where the compound melts. That if it is broad or flattened, then if it is flat, then it means that this compound dissociates significantly. That if you see that peak there is broad, then it means it dissociates significantly. What does that mean? Dissociation means that it breaks, the compound breaks down. For example, let's just take a hypothetical case that A to B. Let's take a hypothetical case that A to B. We break down to 2A plus B in an ideal case. So it says that it dissociates significantly. But that is not, that is something which is still debatable and discussable, because the results still, there's no proper empirical verification that that is true and that there's a real pattern emerging. But in general, it is seen that if it is flat, then it means that this compound will dissociate significantly. In summary, when we have formation of a compound, then the eutectic diagram is not the normal simple eutectic diagram. There will be several eutectic diagrams. And that makes sense because you have this as compounds, so it will be a eutectic diagram associated with the compound. Like we gave the example of hydration. If you have, for example, a salt which it gets hydrated to different degrees, then you'll have several eutectic diagrams associated with those levels of hydration, and so they are fused together, juxtaposed together, so that we have that. And number two, in simple cases of simple compounds, that you'll find in general mostly that the melting point of the compound is higher than that of the individual elements or components, and that is standard. And when we are at the eutectic point, even if we repeated the same thing at that particular point, even if you took another isopleth, the story would be the same. That is, you still have the first primary crystals of A to B and liquid. As you continue, the relative amounts obey Lever-Hutton principle. At this point, there are three phases coexisting in equilibrium, so it is invariant. Temperature will be halted, change will be halted for some time, and then again you start cooling those two solids. So let us stop at that point. We'll pick up with other thermodynamic lectures.